section of that storm is literally rotating. Now, if we look at the bottom picture, very, very similar, the reflectivity is showing us that hook echo where the heaviest rain is wrapping around the mesocyclone. And again, that area in there where there's not much rain, that is the bounded weak echo region. And then you look at that location just north of Moore, and you can see when we're looking at the storm relative velocity, we're looking at the velocity image, and you can see that from the radar site on the far right, just to the top, the red indicates that those winds are rushing away, and on the bottom, the green indicates the winds are moving toward the radar site, and that is where our rotating thunderstorm is. And again, that's how radar detects mesocyclones. Radar doesn't detect the tornado. They detect the mesocyclone. And if the mesocyclone is strong enough and through a deep enough layer of the atmosphere, the radar will then produce the tornado vortex signature, and that is where we get these Doppler-indicated tornado warnings. We haven't quite seen the tornado, but we have a tornado vortex signature, and we think there probably is one developing in that region. One more set of pictures here. Again, this is Tuscaloosa, April 27th of 2011, and you can see the bottom right-hand side, the very pronounced hook echo where the rain is wrapping around the mesocyclone, and even that little purplish area where the line says debris. Using the dual pole Doppler radar, we can tell what type of precipitation is. We can see that's tornado debris in the air right there. And then when you look at the one on the left, you can see the reds where the winds are rushing away and the greens where the winds are rushing toward the radar site. And again, indicating that counterclockwise turning of the mesocyclone. And so if you were an Alabama weathercaster working on this afternoon in April, those would be the radar images that you'd see, and that is how you'd be warning people there could be a tornado on the ground at the university in Tuscaloosa, even if you didn't have a report yet that there's a tornado on the ground. Of course, in this situation, there was lots of reports of tornadoes, but that is a radar image that you'd be looking at. By definition, a tornado then is a violently rotating column of air in contact with the ground. And a funnel cloud is a tornado whose circulation has not quite reached the ground. So for it to be a tornado, it has to actually get down to the ground. So we do have a lot of funnel clouds that dip out from underneath clouds, stretch toward the ground, but don't quite have enough dynamics in place to make it to the ground. And those are tornado clouds. They can create dust swirls and some debris as well, but a tornado has to be in touch with the ground. And the life cycle of a tornado is the funnel stage, the mature stage, and then the decay stage. And the funnel stage is known as the dust swirl, short funnel from the cloud base and a whirling dust to the surface. That mature stage is, of course, its most intense when that funnel is nearly vertical, and then once you start to get those ropey types of tornadoes that you see, that is the rope cloud stage, and that is when the tornado is weakening. Tornado occurrences, no huge shock. By the way, the U.S. has more tornadoes than any other country. Most occur in the spring and early summer, and most in the late afternoon. And this is the average annual tornadoes per 10,000 square miles. And of course, Tornado Alley is going to stretch from the panhandle of Texas through Oklahoma, on up into Kansas, and then into Missouri, Iowa, and Illinois. We also have a nice maximum of tornadoes around the Gulf Coast, and of course here in Central Florida. And as we can see from the number of tornadoes per month, most of them are going to happen in the spring and then on into the early part of the summer. In the spring is when the cold air that's already pushed south for the wintertime is just beginning to retreat. Warm air is just beginning to push north, and it's the combination of the very cold air from winter interacting with the warm air from spring that develops as very strong mid-latitude cyclones, and therefore more intensity to the thunderstorms. A quick peek at the Fujita scale, and then we'll move on to non-supercell tornadoes. It's actually the enhanced Fujita scale, changed about, 8-10 years ago maybe. All scales in weather, whether it's the Fujita scale for tornadoes or the Saffir-Simpson scale for hurricanes, the defining factor, we always think about wind speeds, but the real defining factor is how much damage they do. Because once we start looking at wind speeds above 120 to 130 miles per hour, even in some cases above 100 miles per hour, typically you don't have the type of instruments that can be in those winds and survive. And you certainly don't have the type of instruments that are going to survive a 200 mile per hour wind. So these different categories, these stronger categories, are mostly determined by the type of damage that is done when the tornado goes through. So here's your enhanced Fujita scale from F0 to F1, which is mostly what we see here in Florida, to the F2, 3, 4s, and of course the 5s that they see out in the Tornado Alley area of the Central Plains. And the Central Plains, again, where the cold air from the north and the warm air from the south most easily meet, and it's that combination of cold and warm and moist that gets those violent storms going that creates the very powerful updrafts and the potential for tornadoes. Here is the Fujita scale and its impact on a given farm, and so we can also see the tornado in the background, give us an idea what it likely looked like. F0, you're going to have some branches down, maybe some shingles off of the roof, and it looks like there's a little bit of debris there, pink debris in the yard next to the driveway. You get that EF1, so now you're up above 100 miles per hour. The trees may be uprooted. There may be just a little bit more than shingle damage to your roof. You may even have some plywood pulled off the roof. Maybe a little bit of damage to the lighter building, the little garage there. You can see the car has been moved just a little bit. You get up to EF2, 111 to 113. Now we flip over cars. We demolish weak buildings such as garages and carports. The structure of the roof has now been pulled away. There's been some additional damage done to the house itself. EF3, you have significant damage to the house. EF4, complete damage to the house. And in EF5, the entire home is scraped off the foundation. All that is left is maybe a bathtub and some pipes sticking up out of the concrete foundation, which is why, by the way, if you're ever in the path of a tornado, that interior room, bathrooms, but if you really are in danger, path of a tornado, if you can get a mattress, or several mattresses, and get in the bathtub and cover yourself with the mattresses are going to protect you from falling debris. And if the bathtub is cemented into the floor, now I'm not talking about the upstairs bathroom, downstairs bathroom, if it's cemented into the floor like they so often are, that has the best chance of staying put in these powerful tornadoes. And again, you can see the tornadoes in the background and just how large those EF3, 4s, and 5s can be. Non-supercell tornadoes, meaning either a land spout, or I should say a water spout that develops without any thunderstorm at all, or a land spout or a gustnado that develops with just a normal thunderstorm. Typically, at the surface, you have some pre-existing spin, some boundary that's creating some turning in the atmosphere, and then a thunderstorm develops and moves over that pre-existing spin and pulls that spin up into the atmosphere. So these land spouts are going to be where you get your dust devils and gustnados. We had gustnados during Charlie, where the winds swirling, the eddies being created by the powerful winds blowing through the neighborhoods created swirls, and then as the individual thunderstorms moved over those swirls, the updrafts of the thunderstorms pulled those swirls up, and you got what's known as a gustnado, weak tornado, forming along a line of thunderstorms. Of course, the land spouts and the water spouts, all surface-based. Remember, our tornado from the supercell, it came out of the middle levels of the atmosphere, so these land spouts and water spouts are all surface-based. They tend to be weaker and much more short-lived.
Here in the Andes Mountains, you also have geography playing an important role in severe thunderstorm development. The two air masses collide. The warm, moist air from the Amazon basin collides with the cool air from the South Pole. It mixes, and the warm air is pushed up by the mountains and forms some of the most severe thunderstorms on Earth.
Jim sets off to try and get underneath the center of a developing storm. The lightning is a byproduct of the extreme air movements within storm clouds. Inside the storm clouds, warm, moist air rises. As it gets higher, the temperature drops and the water particles freeze. Some become small ice crystals, others larger slushy ice. In the turbulent storm, the two different types of ice crash into each other and become electrically charged. A huge electric field begins to build up until it becomes so strong it reaches for the earth below. But higher in the atmosphere is a much more elusive, much more exotic form of lightning that even Jim has never seen. They're called sprites. This is a type of lightning that doesn't strike down towards the ground, but instead reaches upwards, sometimes as far as 75 kilometers high into the stratosphere. They're rarely seen because they happen so far above the Earth.